Hello, everybody, and hello, everybody here. Welcome to the 11th session of the Category Theory Seminar at Stellenbosch. So today we're going to be listening to Peter Faul give a talk about inverse semirings and monoidal functors.
Yeah, exactly. Great.
Thank you.
Okay, great. Thank you. And I should mention now, while I remember, that well, this is part of a project that is joint work with Hideo, Graham, and Amorto. But yeah, the work we're doing here, yeah, I guess is yeah. Anyway, it doesn't matter. So okay, so what I'm talking about here in this talk are inverse semirings. Okay, but in order to get an appreciation for what inverse semirings are, we should first talk about what inverse semigroups are, or inverse monoids in our case. So here's the idea. So, okay, inverse monoids. What are they? So in a monoid, we have an identity, but in general, we don't have inverses. Obviously, in a group, we have both an identity and inverses. Now, it turns out there's a situation that exists in between these two settings, and that's where we have sort of inverses in the following sense. So a monoid is, well, let's say inverse if for every element, so for every x element of M, we have this, so there exists a unique inverse which we're going to call x star, and it's going to satisfy, I should put inverse in quotes.
You probably want to write a little bit away from the left, just because.
What?
Oh, that's good. Yeah, that's good.
Fine. Yeah, I can further continue going on. Okay, so if there exists a unique inverse x, that satisfies the following equation. So x star x needs to equal x, and x star x star needs to equal x star. So how is this related to an inverse in any way? Well, notice that if we were in the situation of groups, and this inverse was a real inverse, well, then this would just be the identity. And so we'd have that x equals x, and similarly, this would just be the identity. And so we'd have that x star times the identity was equal to x star. But in our setting, this kind of intermediate thing here, x times x star, need not be the identity. So, so of course, all groups are inverse monoids, but there are more interesting examples than just that. So, for instance, if we take the product, so if we take a product of a group and semi-lattice L, so if we take G cross L, where G is a group and L a semi-lattice, then notice that we're going to have these non-trivial inverses. So if we have an element G comma X, okay, so G comes from the group and X from the lattice, well, then we can multiply it by G inverse comma X, so G inverse being the real inverse in the group G, and yeah, and then in particular, we write out this gx, and we can see that the G inverse becomes the identity. We multiply again by the G, so we recovered G in the first component. And because we're in a semi-lattice, this XXX, they will multiply, it's idempotent. So we just end up with an X there. So, and in fact, you can kind of do the reverse as well. So G inverse X, G of X, G inverse of X, of course, is equal to G inverse X.
So isn't this because L already has that structure, right? And it just takes the product of two things that have that.
Yeah, in some sense. But so the important thing, yeah, so I suppose, yeah, maybe I spoke about groups having the structure, but of course, semi-lattices have the structure as well, but also perhaps they almost have the structure in trivial ways, but in opposite directions. But by combining them, we actually get some nice non-trivial examples. So yeah, notice that what we end up with here in this intermediate phase. So gx, g inverse times x, g inverse of x is going to equal the identity comma x. And we're going to have an element of this form for every element of the lattice L. And in particular, the interesting thing about these elements is that they're idempotents. So 1 comma x times 1 comma x, we can kind of see is just equal to 1 comma x. But this will be true for all inverse semigroups. So, and in fact, it's very easy to see. So if we have x star, and we multiply it by x star, or we just rebracket as x star x times x star, and we end up with x star. So these, when you multiply by this kind of pseudo-inverse, you get not the identity in general, but an idempotent. And that's the really fascinating thing about inverse semigroups, is you've got this semi-lattice of idempotents that lives inside of it. So these idempotents form a semi-lattice. This is not completely obvious. So these idempotents, so rather, yeah, so these, maybe not, instead of these, let me say, the idempotents of an inverse monoid. And yeah, so I've been talking about inverse monoids. This is most often studied in the, or called inverse semigroups, where they don't actually care about having an identity in the first place. But I think you pretty much, in most cases, should have the identity. So the idempotents of an inverse monoid form a semilattice. So we already know that they are, if we were to just consider the collection of idempotents, it's clear that multiplying an idempotent by itself is, of course, idempotent. But in order to show that it's a semilattice, we want that it's closed under multiplication. So when you multiply two idempotents together, you get an idempotent back. And we'll also want that it's commutative. Now, these two results follow from, it's actually quite difficult to prove. So I won't provide the proof yet, but it turns out that in any inverse monoid, whether or not it's commutative or not, the idempotents always commute with each other. And so that allows us to just demonstrate that, yeah, indeed, we get a semi-lattice of idempotents. But, OK, so that follows from some non-trivial result that I'm not showing you the proof for. But we don't need to worry about that, because from now on, we will only talk about commutative inverse monoids. So that all follows for free in this setting. Commutative inverse monoids. Right. And so now we're going to talk in the commutative inverse monoid case. Yes, question.
So you can certainly define the exact same notion as the inverse for a group for a monoid.
What do you mean by that? So
there exists x because there is a 1.
Yeah, sure.
X is equal to 1.
Yes, you can do that, yeah.
And how do you call a monoid like that?
That would just be a group.
Yeah, okay.
Yeah, so yeah, in that case, so yeah, some monoids will be groups, but in this case, yeah, you have these inverses corresponding to the idempotents that live in a monoid. And I think in a group, the only idempotent you can ever have is the identity element itself. And so in a monoid, you can have these other idempotents, and then you can ask for inverses that take you to idempotents, and that's what you get, yeah.
Yeah, maybe it's an inverse form, which is a bit not.
Yeah. So I mean, I did put it in quotes originally, but now I'm just using it like it is an actual inverse. But they are generally called the inverses. So yeah, but think of it like a pseudo inverse. Yes.
So are they always group times semilattice?
No. Well, there's some structural results like this. It needn't be group times semilattice. I think you can take semi-direct products. But there's a slightly more general structure result, like maybe it's like a wreath product of a group and a semi-lattice. But yeah, we don't need to worry too much about that right now. But OK, so in the commutative case, there's something interesting that happens.
But you're going to be giving a structural result in the commutative case, right?
Yeah, I will be. Yeah, I'll be giving another structural result. But yeah, there are these things. This relationship between groups and semi-lattices. In fact, the structural result I'll give will also relate to that in a way, but there are more concrete ones. So the important thing here is that every element. OK, So every element x has an associated idempotent, which is x star. And I'm just going to call that E of x in general. And so when it's in the non-commutative case, you actually have two idempotents, depending on the order you multiply by, because x star x will be different from x star. But in the commutative case, they're the same. Is there something wrong?
No, just see if I can post this.
But okay, so every element has an associated idempotent. And so let's think, what happens if we group together all of the elements that have the same idempotent? So consider, let's call it S, of all elements such that, so let's say we had an inverse monoid. I don't know what is a good letter for that. Let's just call it M. So consider all x and m such that x star is equal to some idempotent E. Okay, so what properties can we expect this S to satisfy? Well, it turns out that it's closed under multiplication. So if we had x and y, which both have this idempotent E, we can ask what is its idempotent? So in order to compute that, we consider xy star. Now, this is kind of, there are a couple of basic results that I'm not going to prove, but it turns out that when you take the inverse of a product, you apply inverse to both parts, but you swap the order, kind of similar to what happens in groups. So this is going to be xy, y star, x star. But again, we're in the commutative setting, so this is just going to be x star, y star. But as discussed, both of those just equal E. So it's going to be E times E, but that's just equal to E. So indeed, multiplying two elements that have the same idempotent together, we keep the same idempotent. And also, this E behaves like an identity. So E of x is equal to x star x. So we've just expanded what the E is. And that's, by definition of these inverses, just equal to x. And similarly, you can, yeah, I mean, that's also just equal to, you can kind of check for yourself that it's equal to xe. So,
Well, it's commutative. So.
yeah, it's commutative, of course. Yeah. But yeah. So, okay, so we get xe. So the point is, the idempotent behaves like an identity. And in fact, then we see, so once this E is like the identity in this subset, well, then the inverse is actually a group inverse, a true inverse, in the sense that when you multiply by the inverse, you get taken to the identity. So this is the structural result that, yeah, is quite important, which basically is saying, so if we're considering an inverse semigroup, we've got this semi-lattice of idempotents, and to each of them, you can consider an abelian group, in this commutative case at least. So there's an abelian group associated to each of these things. And so, I mean, so we kind of have this function, which goes from, let's say, a semi-lattice, well, for now, I guess, spoiler, it's going to be a functor, into abelian groups. So to every element of the semi-lattice, we associate an abelian group. And it turns out that when you take the opposite order, so you kind of treat this the semi-lattice as a category, where if an element is less than another, you have a morphism. And well, we take the opposite of that order. Then we get a functor, or rather, yeah, now this becomes a functor into abelian groups, and that precisely corresponds to a commutative inverse monoid. And so it's kind of really, we've seen that this accounts for all of the elements, but maybe it's not clear that we can actually recover the multiplication that we'd want, or how would we know? We've got basically the semi-lattice and a whole bunch of like disjoint abelian groups, but how do we know how to multiply two elements in different abelian groups? So notice that we will have, let's say we've got an element x, and which is associated to the idempotent E of x, which is not equal to the idempotent E of y, and we have some element y that corresponds to this idempotent. So how would we multiply these together? So the point is, if we were to multiply the idempotents, because we're in a semi-lattice, this will be less than or equal to both E of x and E of y. So we get this nice order structure, and we get that E of x times E of y is less than E of x. But we said we had a functor. So this less than or equal to is actually a morphism from, well, rather we get a morphism from E of x to E of x times y because it's smaller than E of x, and similarly from E of y to V of x times y. And we can use these functions, group homomorphisms that we get in order to define the multiplication. So if we had, so basically, to kind of just give an example, so f of E of x, we get a map, a group homomorphism into f of E of x, E of y. And so now x lives in here. And similarly, we have y lives in f of E of y, and we have a map similarly into this. And so in order to multiply two elements in different abelian groups, we just apply these homomorphisms to the elements x and y, and then multiply them together in this f of E of x, E of y. So that's kind of just a quick sketch of this idea that commutative inverse semigroups can be represented as functors from a semilattice, the opposite of a semilattice, into abelian groups. And so that's all the background that we're going to need before we start talking about this new concept that we've been looking at.
So Peter, this is something known, right?
This is known, yeah. So yeah, this was all just background. So now's the new stuff. So now we want to look at this concept called inverse semirings, which we've now found actually has many other names in the literature, but which this result does not exist for any of the names they use, which is a relief. So the idea is we've got a ring. A ring usually has an abelian group additive structure and a multiplication, a monoid multiplication. But what if we replace that abelian group addition with an inverse semiring? With an inverse semigroup, an inverse monoid, in fact. So yeah, so an inverse. A commutative one. Yeah, absolutely. An inverse semiring. I'll give you a very informal definition, just write it out, is a ring where the abelian group structure has been replaced. By a commutative inverse monoid. So, okay, so we don't want to just be generalizing for generalization's sake. So the reason we considered this in the first place is we have this kind of topological example that, it kind of came up while we were considering topological things, and it ends up having this natural inverse semiring structure. So to kind of not go into all of the details, there's certain, when you try to connect, let's say, the topology of the polynomials, a polynomial ring, to kind of this computational interpretation of topology, it ends up not being quite right. And so what ends up being the case is that you actually want to instead consider the following ring, inverse semiring. So we don't want to just consider polynomials. We want to consider polynomials equipped with a maximum degree. So, sorry, I should say example. Okay, so we want to consider P of x, the elements are going to be polynomials and a natural number n, such that the degree of P of x is less than or equal to n. And so what are our operations going to be? So P of x, comma n, plus Q of x, comma m, is going to be equal to P of x plus Q of x. And then we take the max of n and m. So we want to keep track of what the maximum possible degree is without having to inspect the polynomials. And so without looking at, because notice when you add P of x and Q of x together, you could technically have the degree decrease by having terms cancel. But we want to be able to keep track of this maximum possible degree without having to check whether things have canceled or what the total degree is. And because it turns out it's computationally, let's say, impossible to check that a real number is actually equal to 0 to see that you've actually canceled these coefficients. So that's part of the motivation. So this is the most sensible thing we can do for addition. And for multiplication, it's kind of the obvious thing. So Q of x, comma m, and that's gonna, we just multiply the polynomials together, and we add the maximum degrees. Okay, so the claim is that this is in fact an inverse semiring. So if we have P of x comma n, the inverse is going to be negative P of x comma n. And when we add these together, we're going to get 0 comma n. But we can't ever eliminate that maximum degree. Even though the polynomial is eliminated, we actually computationally can't know that. And so we the idempotents end up being 0 polynomials followed by all possible natural numbers. And so why are the natural numbers?
Because n is the actual 0, right?
There is the actual 0, but yeah, well, let's not get into that. Yeah, the actual 0 is going to be 0 comma negative infinity, the true 0. But we won't worry about that for now. But yeah, just remember that when you add, so if we were to add this to itself, remember we aren't adding the natural numbers. We are taking the max of them. So 0 comma n plus 0 comma n is equal to 0 comma max of n and n, which is just equal to 0 comma n. So that's why these are idempotents, in fact. And so we get the structure of an inverse semiring. Okay, so that's the motivating example. That's we'll come back to this example again and again as we go through more results. But
of course, any ring is also an example.
Any ring is, I mean, there are a number of interesting examples. So idempotent rings are also examples. So these are just ones where idempotent semirings are examples. These are ones where the additive structure is an idempotent. So these are all quite well studied and kind of simultaneously generalized by this notion. And yeah, so you can kind of just explore some of the basic results about rings, and you actually get analogs. So for instance, -1 times an element indeed is equal to, okay, so let me just establish notation. So we're going to now just refer to the inverse. Remember the inverse the inverse monoid structure is on the addition. Okay, so before we were using multiplication, now it's an addition. And so we're going to call the inverse of x negative x. Okay, it's a bit confusing. You need to remember that x minus x may not be 0. It's going to in general be an idempotent. But so -1 times x will in fact be x. And so just
You mean x inverse?
yeah, x inverse. So the point is we want to check that if we were to add -1 times x, we were to consider this expression. We would want that this is equal to x. And using the distributivity, which still holds in our rings, you can take out the x and you get 1 minus 1 plus 1. Now again, this is kind of interesting. 1 minus 1 may not be 0. It will be an idempotent in general, but 1 minus 1 plus 1 will be 1. So this will equal x times 1, and this will equal x. So you recover a lot of the usual things you'd hope from a ring. So it's very well behaved, given up like how much we seem to have given up, basically the true inverses. Yeah, so what we've been looking at in this paper is ideals of these inverse semirings, which pretty much ideals behave very nicely for rings, and they don't behave very nicely for semirings. But we found that ideals of inverse semirings kind of behave more like the ideals for rings. So it's a very well-behaved structure, but that's not what this talk's going to be about. So I just thought I'd put that out there that, yeah, there's some very interesting things to explore with the ideals of these structures. But what we want to do now is we want to generalize. Yeah.
I didn't quite catch what 1 is. Is it 1 comma?
Oh, so in the bounded polynomial case. Yeah, in this case, it would be 1 comma 0. Yeah, so the constant 1, yeah, and it has degree 0. I think, yeah, in that case, it is actually the true, oh, no, sorry, the true 0 is 0 comma negative infinity. So that's why 1 minus 1 in this example is an idempotent.
Actually, constant.
I don't understand that because is negative infinity then one of your outputs?
So it's just.
Well, just by convention, we'll say that the degree of the polynomial, the 0 polynomial, is negative infinity.
So you are
Yeah. There's like a sense in which 0 behaves differently from the rest of the other constants in some sense. Yeah. Okay, so what we want to do now is we want to generalize this result to inverse semirings, because it turns out that there's a very nice way to think about these in these terms. So basically, we want to know, yeah, is there some nice way of thinking about an inverse semiring as some sort of functor into abelian groups? And so the idea is that, well, inverse semirings still have a semilattice of idempotence. You can just take the semilattice of the idempotence with respect to the addition. But they're going to have more structure because
sorry, can't you think of inverse semiring as inverse monoid with an internal monoid? So that's probably how I generalize it.
Exactly. So, but yeah. So the question is, what's going to be the internal monoids with respect to what monoidal operation? And so we're going to discuss that in the day convolution and so on. So yeah. So before for inverse monoids, we had a semilattice of idempotence. Now it turns out we're going to get that we do get that semilattice, but it also has this additional multiplication. So pretty much, yeah, you'll be able to multiply idempotence by each other, and that will, in fact, still preserve being idempotent. I'm trying to think if I know the proof offhand. So if we have an idempotent, in fact, well, yeah, the point is anything times an idempotent is, in fact, an idempotent. So x times, if E is an idempotent, and we want to know if we add it to itself, will this be itself? That would show that this is an idempotent, but we simply just factorize out the x, and we get E plus E. And so that's just equal to xe. So in fact, if you take an idempotent and you multiply it by any element in this inverse semiring, you'll still get an idempotent. So the point is the idempotents themselves form an idempotent semiring. So this ends up being the kind of, well, maybe, yeah, let me actually keep the notation. So it's L plus and times, and the plus will be idempotent when we're looking at only the idempotence, and the multiplication still preserves it. So this ends up being an idempotent semiring. Okay, so the hope is that, yeah, maybe.
Yeah, so the unit now is the idempotent corresponding to 1.
Yeah, indeed. So this ends up not being a sub-inverse semiring because it doesn't preserve the multiplicative unit. But so what we want is, yeah, in some sense, for some sort of functor from yeah, this idempotent semiring of into abelian groups. And what we're going to find at the end is that we want it to be a monoidal functor, because we can think of this as a monoidal category. So what this means, or pretty much what's going on, is the addition is going to give us an order, because again, the addition really is it's like a meet operation. So we get an order, and we can view this as a category, where again, if an element is smaller than another element, we have precisely one morphism between them. And this multiplication ends up having the structure of a monoidal, a monoidal operation on a category. So we can think of this as a monoidal category. And similarly, abelian groups can be viewed as monoidal categories. And so it's going to turn out that inverse semirings are going to precisely correspond to functors from this monoidal category into abelian groups. And so how are we going to see this? So this ends up actually being related to what Zurab was talking about. So if we had, so one way to think of semiring is you consider like, one way to think about these inverse semirings is you take a commutative inverse monoid and you consider internal monoids in this category. And those internal monoids will basically supply the multiplication operation. So in some sense, if commutative inverse monoids corresponded to functors from semilattices into abelian groups, we would think that our inverse semirings correspond to, at least our inverse semirings with lattice idempotence corresponding to L. These are going to correspond to to internal monoids in this category. But in order to talk about internal monoids, we need a monoidal product on this category. So Hom by default does not have some sort of monoidal structure, right? So if we want to talk about internal monoids, we would want to, take a functor f and somehow be able to tensor it with itself, and then consider, for instance, a multiplication from f tensor f into f. But what is this operation going to be for these functors? Now, it turns out there's a general categorical solution to this called the Day convolution. So it says when you have two categories that have monoidal products, you can essentially bring that up to the level of the functors in a certain way. You need some co-completeness, and you need some sort of V enrichment. But in our setting, we're going to be able to do this. So let me sketch to you what's going to happen. So so again, we've got this L plus and times. Let me call the times the usual, like monoidal. We usually write an X with a circle in for a monoidal product. Okay, so we've got this category, and we've also got ab. Okay, and now, we've got, let's say, a functor between them. So, how are we going to now define a tensor product on, let's say, two functors of this form, so f and g? So it ends up being a bit complicated, but so I'm just going to describe what it is on objects to you, and then we're going to, it's quite complicated, but we won't actually unpack all of the complicated categorical aspects of it. We'll instead look at it in our specific example. So if we have f tensor g and we apply it now, let's say c is an element of L. Okay, so remember, this f tensor g needs to be a functor from L into F. So if C is from L, what abelian group should it give? And so what this is in general going to need to be is going to be this. Oh wait, what are these things called again? Coend, C1, C2. The name just escaped me. Okay, so we're going to take a coend, and it's going to be of the following form. So Hom of C1 tensor C2, C, tensor f of C1, tensor f of C2. So here is
G of C2. Yeah.
Absolutely. Yeah, thank you. G of C2. So here's the first issue that we encounter. So technically, in order for this to make sense, so this is a limit or a co-limit we're taking, or a coend we're taking in abelian groups. But what is this? This isn't an abelian group. So we shouldn't be allowed to tensor this with these other abelian groups. And so this is the first, what we end up doing is we take this Hom set and we just generate the free abelian group. Okay, so that's how we resolve the situation that this category is not abelian enriched. Another way of thinking about it is usually this category, the Hom sets, are either empty or singleton sets, depending on if an element's less than or equal to it or not. And you can actually just replace those with either the zero abelian group or the integers. And that's what's going on here. And okay, so what's the intuition? Well, let's look in our case. So this, I've given you this. This is like the general definition for arbitrary categories. But in our case, we've got this kind of interesting situation where there are only two possibilities for this Hom set, or let's say the free abelian group generated by this Hom set. Either C1 tensor C2 is less than C, or it's not. Now, remember, there should be some ops here. So we've actually flipped the order. But so in this situation where C1 tensor C2 is larger than C, this is going to be the integers. And what that's going to do is it's going to leave this unchanged, because tensoring an abelian group by the integers does nothing. And in the situation where C1 tensor C2 is less than C, it's going to be
not greater than C.
Is not greater than C. Yeah. Then it's going to be the trivial group, which is going to actually destroy everything. So what this is saying actually is we're going to be taking this kind of co-limit type structure, but we're only going to care about these abelian groups when the C1 and the C2 satisfy this property that they're greater than the C that is in question here. So sorry, maybe I didn't make this clear, but we are taking this coend over all pairs C1, C2. So all C1, C2, we compare them to C, or the product with C, and yeah, we get this result. So so let's look at, so now the idea is that this will be a monoidal product that works on this Hom category. And so now it's kind of simple in some sense. So without going into any of the details in our specific case, all we're going to do, and it's kind of like obvious that this is true already, just from, yeah, basically how category theory works. So we will simply consider internal monoids in this functor category. And so I will be getting to that. But yeah, so the point is we've got the internal monoids with respect to this tensor product on Hom will be our inverse semirings. But let's get some intuition for, yeah, why this is actually a good notion. So yeah, instead of just kind of seeing this very abstract definition, yeah, why is this the right idea? So yeah, so we want to look at our polynomial case. So what are the idempotents in that setting? So the idempotents are the natural numbers with respect to the max operation. That's the idempotent addition. And then addition ends up being the multiplication. So, yeah.
I'm a bit lost with the C and the C1 and C2. I might have forgotten the relation.
Yeah, so, okay, so what we do so the C is the input. So we're defining the functor F tensor G. So we need to say what it does on all of the objects, basically. And so when we apply it to C, what we do is we kind of, yeah, iterate over all C1 and C2 pairs, such that when you multiply them together, the result is, yeah, well, we're going to compare it to C itself. So C1 multiplied by C2, is it less than or equal to C, or is it greater than C? These are the two cases that we could have. And yeah, that's captured by this Hom over here. And so that is going to then either eliminate everything that comes after it or keep everything the same, just because we're either going to get the integers.
It will be either 0 or 1.
Exactly. It'll be either 0 or 1.
So it's the same as summing across all the C1 tensor C2 less or equal to C.
Yeah, well, it's actually greater than equal to because we have an off. But
yeah. That is true. Yeah, yeah. In the end, in this particular case, that is the case. It's because we have a pre-order category.
It's like convolution product in the group functions on a group.
Yeah, that's what I'm thinking also.
Yeah, yeah,
That's how you define the off structure on the maps of the groups.
Yeah, no, I mean, I think the name kind of references it. It's called the day convolution. So I think the connection is there.
So that Hom is not because it's so weird, but it has not the S, but it's just using to is 0 or 1.
Basically, yes. And so, yeah, again, what we end up doing is in order to actually tensor it with the abelian groups, we take the free abelian group generated on it. But yeah, so that's, so it becomes either the 0 abelian group or the integers, which behaves exactly how you say, either 0 or 1, basically, with respect to multiplication.
There is this little symbol. It's not a sum exactly?
It's an integral. Well, the symbol is an integral sign, but
how do you do it?
So there's some, yeah, I mean, there's some stuff going on here. So
it's a quotient. It's a quotient of like the co-product of all of these things.
Oh, okay.
So you take the co-product of all of them and then you quotient it in a certain way.
So it's some kind of limit.
Yeah, some kind
a co-limit. Yeah. Yeah, but yeah, so I didn't want to describe the exact procedure in which this is done. I'd rather look at it in our specific example of bounded polynomials. So in the bounded polynomial case, the idempotent semiring we get is n, the natural numbers with max and addition. And yeah, so, okay. So now let's look at, for instance, these Homs of C1, so now C1 plus C2, and we're going to be comparing that to C. And so we're basically going to be interested in the cases where C1 plus C2 is greater than C, and as a natural number, and we're going to eliminate any situation where C1 plus C2 is less than it. And so I'm not going to provide the proof here, but it turns out that this entire thing in this setting is going to equal. So basically, after you've done the quotient, what you're going to be left with is the disjoint union, the co-product of C1 plus C2 equal to C of f of C1 tensor G of C2. So so basically, yeah, we consider all of these cases, and the quotienting is going to actually notice. Yeah, we consider all cases where C1 and C2 are larger than C. But after we've done the quotient, it's basically like we're just considering C1 plus C2 is precisely equal to C, and that's what this is going to end up being. And so let's think about now our polynomial case again. So let f be this.
But can we see in that example what you are quotienting with?
Like I don't have the details like on hand right now. Like I didn't. Yeah, I mean it might even be easy. I just didn't think of it ahead of time, and I don't trust myself to derive it in front of you all. But yeah, so now imagine that f is going to be basically this functor that corresponds to our n with max, basically. So our inverse, our commutative inverse monoid on the polynomial. So it's sorry. So it's going to give basically the inverse monoid corresponding to. So f corresponds to this thing where we have p of x comma n plus q of x comma m is going to equal p of x plus q of x, and then the max of n and m. Okay, so this is our f. Now the hope is that if we consider an internal monoid on this f, we're going to recover or be able to recover the multiplication. And so if we consider f tensor f, okay, and some sort of map into f itself, what would this map do? So if we were to plug in some c over here, what this would end up being is a whole bunch of pairs c1 comma c2. Oh, sorry, no. These will be, I'm not doing it right. So the point is we would be able to break this up into a whole bunch of polynomials. So f of c1 tensor f of c2. Okay, but so remember now this f of c1, it gives us polynomials of degree maximum c1, and this f of c2 is going to be polynomials of max degree c2. And so what the multiplication is going to be doing is it's going to be defining a way to take something of degree maximum degree c1 and something of maximum degree c2 and give you something of maximum degree c1 plus c2, which is precisely what we want from this multiplication. And indeed, you will be able to find a multiplication corresponding to this internal monoid, giving you this internal monoid that precisely recovers the multiplication you want. So yeah, I kind of skimmed over a lot of the details for this part, but hopefully it's kind of clear that this deconvolution does indeed give us the data we need to define this sort of inverse semi-ring in this particular setting. And so now the final thing I want to end off on, and I'm not going to provide a proof of this, but this is a well-known result, which is that internal monoids with respect to the deconvolution, oh, what happened there? There we go. They correspond to monoidal functors. Correspond to monoidal functors. So remember, we were looking at internal monoids inside of here to AB, and it turns out that these internal monoids are in one-to-one correspondence with simply monoidal functors. Yeah, so actually, yeah, it's simply just a monoidal functor from L meet dot to AB tensor. And so this is just a well-known result. And so that kind of concludes the proof, basically, that these inverse semirings are nothing more than, monoidal functors. And what's interesting about this is this doesn't actually form the category of all monoidal, of all inverse semirings, because notice that we've fixed in advance this semi-lattice of idempotence. So this only allows us to talk about all inverse semirings that have that same the same underlying idempotence. And one thing that Graham and I are going to publish in another paper is how you can actually recover the entire category of both inverse monoids and these inverse semirings by having a Grothendieck construction that basically, you apply the Grothendieck construction to this two functor that it basically assigns to any semi-lattice this Hom category. You apply that, and then you actually are able to recover something that's equivalent to the usual category, but I'm not going to talk about that now. So that's the talk. Thanks everyone for listening.
So my previous remark was actually in a slightly different direction. So we can also think of a ring as a function from one object from the multiple. Basically, what I was trying to say is monoid acts on acting on that group.
So wait, it's a functor from what?
We can think of a ring as a multiplicative monoid acting on an abelian group, right?
Okay, sure, yes.
Yeah. I think that's more what I went with my previous remark. So, from this point of view, does that where will that take us?
But I mean, a ring is like a multiplicative monoid acting on an abelian group is more general, right? Because it could have like the elements are actually the same, right? In a ring, the elements of the monoid
and when the elements are the same, I imagine you just get an internal monoid.
Yeah. So it's an internal monoid. And the same is true, that an inverse semiring is an internal monoid in.
From this perspective, we don't have to worry about the monoid structure. So
yeah, I feel like your thing is describing more like a module in general, right? And I mean, that is something we've been thinking about, how modules would work. But so you're saying we would avoid, I mean, it sounds like it ought to be more complicated, or like involve more structures, such a characterization of like a module. So I don't see how you'd avoid.
So we don't need a monoidal structure, but I'm not saying I have something concrete in mind, apart from just trying to see if we take this point of view, whether it also gives another way to get the same result.
I would never assume that it kind of induces a monoidal structure that you would then probably want to make use of. So maybe it could avoid it, but I mean, it's not necessarily something we want to avoid, I guess. But maybe I'm not exactly understanding what you're suggesting. Yeah.
So I have two questions. So you said that your inverse, it's when you multiply it by something in both directions, it's an idempotent.
Well, that's not the exact. So the exact definition is that x star x needs to equal x.
But my question is, how far do you have example where? Okay, so
or I don't know if in linear algebra there's this thing called the Penrose pseudo-inverse of the matrix.
Yeah, that's what I was.
And that's an example of this. Yeah.
Right.
Okay. So
my favorite example of this is partial symmetries on a set. They take partial bijections from a set itself. That gives you an inverse partial. So a bijection from one subset of the set to another subset of the set.
Okay.
And you actually have something like Cayley's representation theorem. So every inverse semigroup occurs as a sub-inverse semigroup of the structure Zeron's just described.
And then the idempotents are the subsets. They're identity maps on the subsets.
Okay. And the last one is, so you say that by constanting you get C1 plus C2 equals C.
Yes.
There are situations where you don't get that.
So if it's a different, this is something that arises from the fact that we've basically got a pre-order category as the domain that we're considering. And so yeah, we end up getting this kind of
Yeah,
very
the
nice
question is,
simplification.
do we always get that the sum equals something as opposed to saying less than or equal to or whatever?
You mean in a fully general setting?
I think we probably do.
Yeah.
I think we do, but we need to check.
Yeah, we haven't
always get this result.
Basically, all we've done is we've like got the general result and we've tested it for this particular case of the natural numbers. So we haven't looked at it more generally.
No, because it would be good because I think if you put that it's equal, then it links with like what's even group state. Those kind of.
Oh, so in the group case, do they have like an equality instead?
Yeah, for convolution, you're usually taking the sum.
Oh, yeah.
Or whatever.
Yeah.
Over the things where they equal.
Yeah, no, that would be nice to make that. Yeah, like.
And if it does not, it would be interesting. Have an example.
Yeah.
Not.
Essentially, what happens in this case, like with the polynomial case, is you can end up adding together things that have like larger degree. But then when you kind of quotient, like what the quotient does is it ends up identifying, like essentially kind of getting rid of the things that are higher degree. Like the quotient needs to make them agree with the
So I think
the things of lower degree. So all that extra information of the higher degree things ends up getting like destroyed and just identified with the things with the smallest possible degree, where it's actually the degree equals C rather than as large than C.
Yeah, so I think like to explain what Graham's talking about, I think so. If we have these polynomials p of x comma n and p of x comma m, technically we can also consider these elements p of x, so literally the same polynomial but have n plus 1. You can just increase the degree, but it hasn't changed the polynomial. We just have weakened our knowledge of the boundedness of it. And similarly, you could do something for this, so you could increase by k or something. And you're going to want, when you multiply these, that there's agreement basically between what we do in the first components. So when we multiply this, yeah, we want, well, in our case, we want p of x times q of x. But in general, yeah, whatever happens, yeah, in these cases, we're going to want to agree.
Yeah, but you are right. You're right. In general, it is going to be equality. I'm pretty sure. If you just think about it from the point of view of the monoidal functors,
yeah.
So you're right. It will end up, when you take the quotient, it will always end up being this thing where you say equals.
Yeah, so it seems to
I don't
become
know
exactly
what
that.
your M is, because I didn't get
Those are just like the natural number degrees, which we can.
No, I think you mean the function M.
Yeah.
Oh, okay, yeah. Yeah, that ends up being the multiplication.
So to define this function M from this co-product of these things, you can just define it for every component. And then in the case of this, so you just say for whenever for any kind of pair of degrees that add up to your degree C, you're going to just have you need a way to multiply a polynomial of degree C1 and a polynomial of degree C2 and get a polynomial of degree C. And in our case, we know how to do that in the example.
Yeah. I don't know if there are any questions online. Doesn't seem to be anything in chat. But yeah, otherwise then, yeah, I mean, thanks for listening. Yeah.